Imagine you're looking into a glass laboratory dish, right? And you're observing this tiny three-dimensional cluster of living human brain cells.
Just floating there.
Yeah, exactly. And you send a mild electrical shock into the dish. The cells react violently. It's just a chaotic burst of electrical noise. But then you do it again the next day and the next.
And by the fifth day, they don't panic.
Right. They process the signal quietly,
Mm-hmm.
efficiently. They've actually physically rewired their own synaptic connections to handle the stimulus. I mean, they haven't just reacted, they have learned.
Which is an incredibly heavy concept.
It really is. Welcome to the Common Room at the little station on Commercial Street in Atchison, Kansas. You are listening to a special broadcast on Chesterton Radio. I'm glad you're here.
We've got the fire going, the streets outside are completely empty, and tonight we are looking at a stack of sources that sit right on the bleeding edge of modern science. And I'd say existential horror, too.
Oh, absolutely existential horror. Because in this deep dive, we are looking at the dawn of organoid intelligence, or OI. And we're going to examine how an 82-year-old radio thriller somehow completely predicted the exact moral and philosophical abyss we're staring into right now.
It's wild, because the reality of organoid intelligence is just really difficult to overstate. We aren't talking about theoretical biology here.
No, this is happening right now.
Exactly. Scientists are actively cultivating human brain organoids from stem cells. These are living, pulsating neural architectures. And they aren't just, observing them through a microscope. They're fusing this biological tissue with microelectrode arrays.
You're creating hybrid systems, basically biological computing.
Yeah, and the Johns Hopkins University Center for Alternatives to Animal Testing has already established a massive central hub for this research. I mean, by October 2026, the entire global scientific community is converging at the Bloomberg Center in Washington, D.C.
For the inaugural International Conference on Organoid Intelligence.
Right. Researchers from everywhere are submitting these abstracts detailing how human neural tissue might actually become the bedrock of our next generation of computers, neuromorphic hardware built out of us.
Build out of human cells, which is mind-blowing. But here's the thing. Decades before Johns Hopkins built a hub for this, decades before we even conceptualized cultivating stem cells into cortical structures, the golden age of radio presented us with this terrifyingly accurate thought experiment.
It's almost uncanny how well it holds up.
It really is. So we are talking about the 1944 broadcast of the thriller series Suspense, specifically a two-part production of Kurt Siodmak's story Donovan's Brain, starring Orson Welles.
A classic.
I listened to this artifact recently, and you guys, it is just a masterpiece of audio dread. The sound design alone is incredible. But the question we need to wrestle with tonight with you is whether this piece of pulp fiction actually stumbled upon the blueprints of the biological computer.
The blueprints and the ethical nightmares. Because to really evaluate that, we have to isolate the underlying worldview of the play's protagonist, Dr. Patrick Cory.
Played by Orson Welles.
Played brilliantly by Welles, yeah.
Yeah.
Because the conflict in Donovan's brain, it doesn't initially start out about a monster. It's about a philosophy.
Right, the mechanistic philosophy.
Exactly. Cory's older colleague, Dr. Schratt, explicitly condemns Cory for it. Schratt is sort of the moral compass, and he believes life contains some spark from a higher domain, something completely intangible.
Like a soul, essentially.
Yeah. But Cory believes life, and specifically the brain, is absolutely nothing more than organic machinery, chemicals and test tubes.
Which Cory demonstrates in the most brutal way possible in the opening scenes of the play. Orson Welles plays Cory with this chilling, just clinical detachment. He basically buys a capuchin monkey from an organ grinder on the street.
And brings it right into his lab.
Yeah, he pets it until it falls asleep in his arms, and then smoothly kills it with a surgical lancet. But the goal isn't just to kill the monkey. He wants to harvest the brain completely intact.
And he succeeds. He basically builds this makeshift, grotesque life support system in a glass jar to keep the extracted brain alive.
Using what he calls a variation of Carell's mechanical heart, right?
Right. And the anatomical precision that Siodmak wrote into the script is actually quite striking for 1944. Cory bathes the tissue in blood serum. He attaches rubber tubes to the vertebral and internal carotid arteries.
Wow.
And then he uses a rotary pump to force the serum through the circle of Willis.
Okay, I actually caught that reference to the circle of Willis when I was listening, but I fully admit I had to look it up. It's essentially a biological failsafe, isn't it? Like a ring of arteries at the base of the brain.
That's spot on. The circle of Willis is an arterial anastomosis.
And wait, a what?
Anastomosis. It just means it's a circulatory network where different blood vessels connect together. In a living human or a primate, if one of the major arteries supplying the brain gets blocked, that circular structure allows blood to flow around the blockage.
So it still reaches the vital tissues.
Yeah, exactly. And Cory basically uses it as a ready-made plumbing manifold for his jar experiment. By pumping his artificial serum into that circle, he guarantees the oxygen and nutrients are distributed evenly throughout the entire disembodied brain.
So Schratt, the older doctor who walks into the lab, sees this monkey brain floating in a jar, and he's just disgusted. He challenges Cory. He's like, how can you possibly know this tissue is still alive if it's completely disconnected from a body?
And Cory's answer is pure bioelectricity. He's hooked the brain up to an encephalograph, but he modified it with an amplifying system.
Right, so he isn't just measuring the infinitesimal electrical impulses, he's actually translating them into sound, which creates this rhythmic thumping static in the background of the entire broadcast.
It's super unsettling. It's literally a purely electrical heartbeat.
Yeah, and then Cory taps on the glass jar.
Yeah.
And the rhythm of the static changes.
The isolated brain is reacting to the external physical stimulus.
Exactly. And Cory uses this to prove his mechanistic philosophy to Schratt. He argues the tissue doesn't feel pain, it doesn't have a soul, it is simply biological machinery reacting to input. You tap the glass, the electrical output alters. That's it.
And this is where it gets crazy, because the parallel between Cory tapping on that glass jar in 1944 and what bioengineers are doing right now in 2026 is just staggering.
It really is. Let's look at the actual modern science for a second. Obviously, researchers today aren't kidnapping monkeys off the street.
No, thankfully. They are using human-induced pluripotent stem cells. They basically guide these stem cells to develop into specific types of brain tissue.
So the literature we're examining for this deep dive frequently references these two things, Lancaster and Pashka models. Broke those down for me. When we say human brain organoid, what exactly are you and I picturing on the lab bench?
Well, the methods dictate the structure. So a Lancaster model developed by Madeline Lancaster is often called an unguided cerebral organoid.
Unguided meaning they just let it grow.
Basically, you embed the stem cells in a scaffold, usually this protein mixture called matrigel, and you just allow them to self-organize in a 3D space. They spontaneously form various brain-like regions.
Okay, and the Pasha model?
Pioneered by Sergiu Pașca. It takes a different approach. It uses directed differentiation. The scientists use specific chemical signals to force the cells to become very specific types of tissue.
Like targeting a specific part of the brain.
Right, like a cortical spheroid.
Right.
So it's mimicking the human cerebral cortex specifically.
Okay, got it. So they take these tiny lab-grown cortical structures and they place them on microelectrode arrays, MEAs.
Yes, and MEA is basically a grid of microscopic electrodes. It functions exactly like Cory's encephalograph in the jar, but obviously with vastly higher resolution. It sits beneath the organoid and captures the minute voltage changes as the neurons fire.
And just like Cory, these modern researchers are trying to figure out if the electrical activity they're measuring actually means anything. Like, is it just random static or is there a structure to it?
Which brings us to the first paper we have from the ArcSIF preprint server. It tackles this directly. It's called Emergent Topological Structure in Spontaneous Brain Organoid Activity.
Yeah, but reading this paper feels like hitting a mathematical brick wall. I mean, they are tracking recordings of anywhere from 26 to 234 simultaneously sorted neural units.
It's a lot of data.
It's a ton. And to understand if these neurons are organizing, they use something called persistent homology, and specifically a Vietoris-Rips filtration. We cannot skip over this as much as I want to. How does this math actually prove the organoid is doing something complex?
Okay, so it requires us to move away from thinking about biology for a second and start thinking about topological data analysis.
Okay, I'm with you.
Imagine you have 200 neurons flashing. You want to know if they are flashing together in a meaningful circuit or if they're just firing randomly. Persistent homology is a way to find shapes in high-dimensional data.
Now, by shapes, you don't mean a physical square or circle of cells sitting in the dish, right?
No. We mean shapes in the data itself, which represent relationships. The Vietoris-Rips filtration is essentially the rule book for drawing lines between these flashing neurons.
How does the rule book work?
You set a threshold, say, a specific tiny window of time. If neuron A and neuron B fire within that exact microscopic window, the algorithm draws a line connecting them.
Okay, I follow that. It means they're correlated.
Right. Now you slowly increase that threshold window. As the window widens, more and more neurons are considered correlated. So the lines begin to connect to one another, forming triangles, tetrahedrons, and more complex geometric structures.
Which are called simplices, I think.
Yes, simplices. Persistent homology looks for structural features that persist, meaning they stay stable and don't just collapse into noise as you change that threshold window.
Okay. And the paper specifically focuses on what they call the first homology, or H1.
Exactly. H1 represents a one-dimensional hole, or a loop. If you find a robust H1 structure in the data, it means a signal isn't just bouncing back and forth between two cells.
It's traveling in a circuit.
Yes. It's traveling through a distinct circuit of neurons and looping back around. It indicates a coordinated, highly complex network.
And the researchers actually found these H1 loops significantly above the baseline noise in 14 out of the 18 data sets they analyzed. It's huge.
It is.
But the part that really caught my attention was their discovery of a non-redundant core.
Ah, yes. That is the crucial finding right there, because it proves the resilience and specificity of the biological network.
Explain how they proved that.
So if you take the data and you randomly remove neurons, basically simulating random cell death,
Right.
the H1 loop structures still survive. The network finds a way around the damage.
It self-corrects.
Yeah.
Mm-hmm.
But if you identify the specific highly active neurons that are actually carrying the primary signal, and you intentionally remove those specific ones from the dataset.
The topological structure collapses entirely.
Exactly, it falls apart. The network relies on a specific non-redundant core of cells that have organized themselves to carry that specific electrical pattern.
It's not an accident of physics.
Not at all. Living human neural tissue, sitting on a microchip, entirely isolated from a human body, inherently builds complex, resilient topological structures completely on its own.
Okay, I have to push back here, though.
Go for it.
I understand the math proves there are electrical loops. And I understand the tissue organizes into this non-redundant core. But I feel like we run the risk of falling into Cory's exact trap of confusing electrical reaction with an actual mind.
That's a fair point.
Like, is this structure actually thinking? Or is this just the biological equivalent of water settling into a puddle?
I like that analogy.
Because if I pour water on the ground, gravity and the topography of the dirt force it into a very specific structured shape. But the water isn't thinking about being a puddle, right? It's just following the path of least resistance.
Right.
Are these neurons just following chemical and electrical paths of least resistance, and we're just projecting intelligence onto it because it looks like a brain?
That is an excellent distinction, and I should say the scientific community is highly sensitive to exactly that. A spontaneous electrical loop in a Lancaster model organoid is not a thought.
It doesn't mean anything.
Exactly. It lacks semantic content. It doesn't mean anything. It is, exactly as you said, a structural dynamic. The cells are doing what they are biologically programmed to do, which is to reach out and form synapses.
So where is the line then? If a puddle isn't thinking, and a spontaneous electrical loop isn't thinking, what elevates this tissue to the level of organoid intelligence?
The line is crossed when the tissue demonstrates adaptation based on external input. Water doesn't learn from being poured. A puddle doesn't reshape itself in anticipation of the next rainstorm.
Oh, but neural tissue does.
It does. The transition from biological material to a biological computer happens when the network begins to take in information, retain it, and fundamentally alter its future behavior based on that memory.
Which brings us perfectly to the second scientific paper. And this is the point where the researchers stop just listening to the organoids and they start talking to them.
This is where it gets slightly unnerving.
Yeah, it does. So the paper is titled Stimulus-Evoked Network Dynamics in Human Cortical Organoids. And they built a graph computational framework, which, from what I gather, is just a very sophisticated way of mapping out how the entire neural network reacts when it gets shocked.
Basically, yeah. They aren't relying on spontaneous firing anymore. They are actively sending targeted electrical stimuli into the tissue via the MEA and then tracking the cascade of reactions.
And the results here are just staggering. So they took a developmentally matched, stimulation-naive organoid.
Meaning it had been growing for 7 days, but they had never once shocked it.
Right. It had never received external input. And when they finally stimulated it for the very first time on day 7, 93% of the neural array engaged in this massive synchronous burst.
It's the biological equivalent of a system-wide panic, a chaotic, just overwhelming response where nearly every available neuron fires simultaneously.
But then they compared that reaction to organoids that had been stimulated previously. So if an organoid had been subjected to the exact same electrical stimulus 5 times prior, its reaction on the next attempt was completely different.
Barely reacted.
It only engaged 10% of its array, from 93% down to 10%. The researchers call this repeated stimulation depression.
Yes.
Explain the mechanism here for us. How is the tissue physically depressing the signal? Where does all that electrical energy go?
Well, we have to look at how neural networks maintain homeostasis. When that naive organoid is shocked, it lacks the infrastructure to process the signal, so the electricity just triggers everything all at once.
Total freak out.
Right. But neurons are metabolically expensive. Firing 93% of the network requires massive amounts of cellular energy. So over the course of those 5 repeated stimulations, the tissue is actively remodeling itself to conserve that energy.
Remodeling how exactly? Are cells dying off?
No cells are dying. It's synaptic plasticity. The network is likely pruning away extraneous excitatory connections and simultaneously strengthening inhibitory synapses.
It's building a circuit.
Exactly. It's building a dedicated, highly efficient, localized circuit specifically designed to process that exact stimulus without waking up the rest of the network.
The paper actually noted something fascinating about the signal propagation. They said the, quote, peak latency versus distant slope was 0.
Yeah, that is a highly technical observation, but it has profound implications.
What does a slope of 0 actually mean in this context?
Well, if the slope were greater than 0, it would mean the signal takes time to travel from the stimulation point across the organoid. It would look like a wave moving across a pond, rippling outward.
But a slope of 0 means there is no measurable travel time.
Correct. It means the response is a fast, near-synchronous burst within just that 10% of the network. The cells aren't passing a message along a lengthy, sophisticated pathway. They have localized the response tightly.
So they basically built a shortcut.
Yes. The fact that the daily stimulation progressively depressed and spatially contracted the evoked response proves the tissue is adapting. It remembers the stimulus, realizes it isn't a threat requiring a system-wide alarm, and builds a dedicated circuit to handle it efficiently.
So it's learning.
By any functional biological definition, this tissue is learning.
You know, it's like moving into an apartment right next to elevated train tracks.
Oh, I've been there.
Right. So the very first night at 2 a.m., a massive freight train rolls past your window. You shoot out of bed, your heart rate spikes, adrenaline floods your entire system. That's the 93% engagement. Your entire biological system is reacting to a massive, novel stimulus.
Because your brain perceives it as an immediate threat.
Exactly. But you live there for a month? A train goes by at 2 a.m., and you don't even twitch. You might not even wake up. Your brain has adapted. It has suppressed the reaction down to 1% engagement because it learned the train doesn't require an adrenaline spike.
It conserved the energy.
Yes. And the neural tissue sitting on the microelectrode array in the lab is doing exactly the same thing. It is literally learning to ignore the train.
And this forces us into a very uncomfortable philosophical corner, I think.
Oh, totally.
If a piece of living human neural tissue sitting in a laboratory incubator learns, adapts, and physically rewires its own architecture based on an external memory, when does it cease to be merely laboratory material?
Right. Is intelligence simply the mechanistic ability to adapt to a stimulus? Or does intelligence mandate consciousness?
Does the organoid know it is adapting?
Exactly. And modern researchers are incredibly disciplined about this. I mean, they constantly reiterate that organoids are not conscious. They do not have an ego, an I, or subjective experience. They are just biological processors exhibiting plasticity.
But in Kurt Siodmak's 1944 thought experiment, that safety rail doesn't exist at all.
No, it is completely gone. Because Dr. Cory doesn't have a blank slate Lancaster model organoid. He has the fully intact brain of William H. Donovan.
The narrative pivot in Donovan's brain is so good. It happens when Cory goes from merely keeping the tissue alive to actually attempting communication.
Right, because there's a plane crash near Cory's lab. And Cory illegally harvests the brain of Donovan, who was this ruthless, megalomaniacal Wall Street millionaire. He secretly hooks Donovan's brain into his makeshift mechanical heart system.
And at first, the encephalograph is just reading delta waves. The specialist Cory consults says this indicates the brain is asleep, likely in a profound state of biological shock from being severed from the body.
But Cory is obsessed. He just leans over the jar, tapping on the glass, just like he did with the monkey, and he wakes it up. The delta waves shift. The isolated brain actually regains consciousness.
Cory basically moves a cot into his laboratory. He spends days in this fever state of scientific hubris.
Which Orson Welles plays so well. The heavy breathing, the muttering.
It's brilliant. He creates a simplified Morse code, combining physical taps on the glass jar with the vibrations of his voice. He's desperately trying to establish a feedback loop with this isolated mind.
I mean, it's the ultimate 1940s version of the graph computational framework we just talked about. He is sending a stimulus and demanding an adapted response.
And eventually, in a truly terrifying scene, he actually gets it.
He does. He wakes Shrat up in the middle of the night. He stands over the jar and issues a command in his Morse code. He says, quote, "If you understand, think 3 times of the word talk."
And the encephalograph just hums. The delta wave pattern distinctly alters. The machine translates the electrical spikes, and you hear it. The brain thinks the word talk 3 separate times.
Cory has achieved contact. But this is where the pulp thriller begins asking deeply unsettling questions about the nature of identity.
Because in the real world, an organoid is a cluster of unguided stem cells. But Donovan's brain brings an entire lifetime of memories, personality, and ruthless ambition right into the jar.
Which leads us to the concept of the parasitic mind. Intelligence operating completely independent of the person. Because Donovan's brain doesn't remain static in that jar, it begins to grow.
Cory actually documents in his casebook that the brain has sprouted 2 distinct nodules of new cells right on its frontal lobe.
And the electrical potential being measured by the encephalograph absolutely skyrockets. It jumps to 510 microvolts, then eventually hitting an unprecedented 1450 microvolts.
Without the physical limitations of a skull or a central nervous system to support, the brain is becoming vastly more powerful than it ever was inside a human body.
And as the electrical potential of the brain in the vat rises, Dr. Cory's own behavior begins to warp. Sidemak portrays this takeover with such brilliant subtlety at first.
Yeah, he does.
Cory starts smoking cigars. Specifically the brand Donovan smoke. Even though Cory has always loathed cigars, he dismisses it as stress.
But then it escalates.
It does. His wife Janice wakes him up because he's moaning in his sleep. She points out he has ink stains on his left hand. And Cory is strictly right-handed.
He goes to his desk, looks down, and sees that he has written William H. Donovan's signature flawlessly over and over again with his left hand.
And his speech patterns alter. He begins repeating Donovan's catchphrase, which is just this low, menacing, sure, sure, sure.
And Orson Welles' vocal performance shifts entirely here. He loses the clipped, scientific cadence of Dr. Cory and totally adopts the rumbling, arrogant, domineering tone of the dead millionaire.
It gives you chills, because the horror here isn't physical violence, not yet anyway. It's the violation of the self. Donovan's localized storm of electrical potential is so massive that it is telepathically dominating Cory's mind.
The brain in the jar is literally overriding the motor and speech centers of Cory's own brain.
Donovan actually forces Cory to travel to the city, manage Donovan's illicit financial empire, and write checks in Donovan's name to fund the laboratory.
And when Cory's wife Janice realizes the truth and tries to intervene, the brain recognizes her as a threat to its survival. So it forces Cory to drive Janice to a psychiatric clinic and commit her to a madhouse.
Okay, I want to stop here for a second and wrestle with what Siodmak is actually suggesting, because it relates directly to the core anxiety surrounding modern brain-computer interfaces.
Let's do it.
Shrat warned Cory at the very beginning not to reduce life to a mere matter of chemicals and test tubes. Shrat argued for a higher domain, right? But the terrifying truth of Donovan's brain is that Shrat was wrong. Cory's reductionism works.
Yes. It is the most unsettling philosophical argument of the entire broadcast.
Because Donovan's brain survives amputation. It thinks, it plots, it wields power. Siodmak is suggesting that a human being is ultimately reducible to the organic machinery of the brain. There is no soul that departs the moment the heart stops. If you can maintain the oxygenation of the gray matter, you save the man.
It's a bleak outlook.
Do we actually believe that, though? If you strip away the arms, the legs, the heartbeat, the breath, all the sensory input of the skin, do you just get a pure, distilled version of the identical person? Or does the act of stripping away the body inherently strip away our humanity?
Well, if we analyze Donovan's behavior post-extraction in the story, it heavily implies that it strips away the humanity. The intelligence survives intact, sure, but without the grounding elements of the human experience, without the physical limitations of fatigue, vulnerability, or somatic empathy, the intelligence becomes something completely monstrous.
Right. Donovan in the jar is no longer a man. He is pure, unadulterated sociopathic ambition.
He is a localized machine for processing power, which makes him the ultimate dark reflection of our modern organoid intelligence pursuits.
Because today, researchers at Johns Hopkins are trying to build biological computers to process vast amounts of data efficiently.
Yeah.
But in 1944, Syed Mack imagined a biological computer that processed human greed.
And that insatiable greed drives the narrative to its tragic climax. The brain possesses a staggering intellect, but it realizes the fundamental vulnerability of its own existence. It cannot rule a financial empire from a glass vat forever.
It requires a permanent physical vessel.
Right. And the climax of this radio play is absolutely brutal. Schratt, the older doctor, finally realizes the extent of the brain's control over Cory. He sneaks into the laboratory while Cory is asleep, intending to pull the fuses and shut off the rotary pump.
He is going to kill the brain.
But the brain senses his intent. The delta waves roar, and the brain completely paralyzes Schratt with its telepathic output.
And in this demonstration of absolute biological supremacy, the brain forces Schratt to put his own hands around his throat and strangle himself to death.
Which is horrifying. The brain in the vat exerts more motor control over Schratt's nervous system than Schratt does himself.
Cory wakes up to find his friend dead, and through the psychic link, he finally comprehends Donovan's true cosmic plan. See, Cory had been suffering from this recurring dream of a faceless giant presiding over the earth, with millions of people marching past in review.
A total god complex.
Yes. The brain intends to graft itself onto a young, vital body. It plans to live on, jumping from host to host, ruling mankind for centuries. And the chosen host for the very first graft is Cory's own son, David.
Which is a fascinating divergence from the source material that really highlights the power of this specific audio adaptation.
How so?
Well, if you read the original novel or look at the later film adaptations, the climax is usually quite different. Donovan often tries to force Cory to murder a young girl who is legally interfering with his finances, and Schratt attempts to resist the brain's hypnotic control by desperately reciting a nursery rhyme.
Oh, wow. I didn't know that.
Yeah, but the 1944 Suspense production discards all of that for something far more intimate and devastating.
It makes it a family tragedy. Donovan doesn't just want an obstacle removed. He wants to steal the body of Cory's child. And it forces Cory into an impossible, horrific corner.
Because Cory knows he cannot simply walk across the room and smash the jar.
Right. The moment he forms the intent, the brain will paralyze him, just as it did Schratt. He has to outsmart a telepathic superintelligence. And to do it, he falls back on the very mechanistic biology that started the nightmare in the first place.
He finds the one vulnerability the brain cannot overcome with sheer electrical potential.
Blood type.
It's so brilliant.
Cory tells his son, David, that they need to replenish the blood plasma feeding the brain's life support system. He asks David to provide the donation, but Cory knows a biological reality the brain has totally overlooked. David has a different blood type than Donovan.
It is a brilliant tragic irony. The brain has mastered telepathy. It has evolved beyond the need for a body. It can puppet a man across a room, but it remains entirely slavishly dependent on the mechanistic reality of human blood compatibility.
It cannot process the wrong antigens.
Exactly.
But the true horror is how Cory has to deliver the poison. Because to maintain the deception, to keep the brain from sensing his betrayal, he has to actually perform the transfusion.
Right, he can't just think about poisoning it or the brain will stop him.
So, while under the overwhelming telepathic compulsion of Donovan's mind, Cory operates. He cuts into his own son. He severs David's spinal cord on the operating table, murdering him, ensuring that David's incompatible blood flows directly into the rotary pump and feeds the brain.
He kills his own son to poison the monster.
The incompatible blood hits the brain. The tissue begins to die. The telepathic hold fractures, and Cory is finally free from the compulsion. But the cost is absolute.
His friend is dead, his wife is locked in a psychiatric ward, his son is murdered by his own hands, and his soul is permanently stained by his hubris.
Cory writes one final, despairing entry in his casebook. He walks back into the laboratory, smashes the apparatus, destroys the brain, and kills himself.
The broadcast ends with this cold, clinical news report from an announcer stating that Dr. Cory and his son were found dead in the laboratory, surrounded by strange machinery in a rapidly decomposing human brain.
Cory pays the ultimate price for believing life is just chemicals and test tubes. And this dark, violent fiction brings us right back to the glaring reality of 2026.
It really does.
Obviously, we're not dealing with the telepathic brains of dead millionaires. We're not fighting off rogue consciousness trying to hijack our bodies.
Yeah.
But we are dealing with the undeniable dawn of living computers.
Yes, we are.
We are dealing with human neural tissue, kept alive by artificial means, responding to stimuli, physically rewiring itself, and learning.
Which is exactly why that Johns Hopkins C8 Hub isn't just a gathering of bioengineers and computer scientists. They are actively integrating ethicists into the core of their research.
They have to.
They are explicitly trying to build a framework for the, quote, ethical deployment of OI technologies before the technology totally outpaces our morality.
Because the economic and technological push toward organoid intelligence is basically unstoppable at this point. Right now, silicon AI, large language models, and neural networks on microchips is dominating the global conversation.
But silicon has hard physical limitations. To run massive AI models, you need data centers the size of aircraft carriers.
And you need vast amounts of cooling water to keep the servers from melting.
You need gigawatts of electricity.
Contrast that with biology. The human brain runs on roughly 20 watts of power.
20 watts. That is a fraction of the electricity required to power a standard incandescent light bulb.
Yet on 20 watts, a biological brain is capable of complex plasticity, associative learning, and intuitive leaps that the most advanced silicon supercomputers still struggle to simulate efficiently.
We are going to build neuromorphic computers out of human organoids because the energy efficiency and processing power are just too massive to ignore. It is happening.
But this is where the bioethical debate enters the gray area. And I want to pose this question directly to you, the listener. If a biological computer grown from human stem cells, can learn, process data, adapt to its environment, and hold a physical memory of a stimulus, could it someday deserve moral consideration?
It is the fundamental, unresolved question of organoid intelligence.
Let's frame it plainly. If you have an AI running on a silicon microchip and you decide your company doesn't need that specific model anymore, you turn it off. You pull the plug. The electrons stop flowing.
You have deactivated a machine.
Right. No one holds a funeral for a calculator. But if you have an advanced biological computer grown from human tissue, humming with topological loop structures, actively adapting to stimuli, and you decide you don't need it anymore, you can't just flip a switch.
No, you can't.
You have to introduce toxin. You have to pour bleach into the vet. You have to actively destroy living, learning human tissue. If you pour bleach into a biological computer, are you killing something?
And if we agree that you are killing something, what exactly are you killing? It is clearly not a human being. It has no body, no rights, no subjective self.
But can we comfortably say it is just a machine?
As we've discussed, it learns. It adapts its physical structure to maintain homeostasis. It exhibits an inherent biological drive to persist.
The ethical frameworks we have relied on for centuries are rigid binaries. An entity is either an object or a subject. It is either a machine or it is a life. Organoid intelligence exists entirely in the unprecedented gray area between those two definitions.
Which is why an 82-year-old radio drama still possesses such a terrifying bite today.
When you listen to that 1944 broadcast, there is this incredible, almost surreal juxtaposition. You have Orson Welles delivering a haunting, sweaty, intense performance of a scientist descending into total moral collapse, committing unspeakable atrocities in the name of progress.
And then, right in the middle of the tension, the broadcast cuts to the announcer.
The man in black.
Right, who cheerfully starts selling Roma wines from California.
The commercial breaks are truly jarring. Salute your health, senor. Try an inexpensive bottle of tangy, appetizing Roma sherry.
It is a stark reminder of the culture of the era, the absolute normalcy of consumerism, wrapped right around a story of existential nightmare.
It's the ultimate contrast. And it forces you to ask, why do these stories matter? Why are we sitting here by a dying fire, reading a pulp sci-fi script from the 1940s while debating the 2026 International Conference on Organoid Intelligence?
It is because fiction forces us to look at the hubris of the creators, not just the math of the creation. The scientists publishing on ArcSave are looking at Vietoris-Rips filtration and peak latency slips.
They are looking at the math.
But Kurt Siodmak was looking at the man holding the scalpel.
Siodmak understood that the danger isn't necessarily that the creation will wake up and turn into a telepathic monster. The very real danger is that the creator might lose his own humanity in the relentless pursuit of knowledge.
Dr. Cory didn't start his experiment wanting to murder his own son. He started with genuine scientific curiosity. He wanted to prove that neural tissue could perform functions outside the constraints of the body.
The road to hell is always paved with scientific curiosity. We are stepping into a future where we will be growing our own computing hardware. We will be teaching biological human tissue how to process our data, manage our systems, and solve our problems.
And as we navigate this incredibly complex new frontier, we will have to rely on those ethicists at Johns Hopkins just as heavily as we rely on the bioengineers. Because the technological capability to build these systems is already rapidly outpacing our philosophical frameworks to understand them.
I want to leave you with a final thought tonight. Something to mull over as you watch the embers in the fireplace fade. Something that builds on the science and the fiction we've explored, but looks strictly forward.
It's a question we all need to answer eventually.
We've spent the evening asking if biological computers deserve moral consideration. We've asked if learning requires consciousness, and if a human being is reducible to the machinery of the brain. But perhaps the most important question isn't whether we can build a computer out of living neurons.
No, it is whether when something living begins to think, we will still know the difference between a machine, a mind, and a man.
Because if we build computers out of ourselves, we may find that the line separating the tool from the creator has vanished entirely. Broadcasting from the common room at the little station on Commercial Street in Atchison, Kansas, Chesterton Radio. Stories, ideas, wonder. Good night.